Welcome everyone, my name's Steve Brooks and I've written the Construction Site Electrical Systems course. I've tried to write this course to make it suitable for all abilities, even for people without an electrical engineering background. In this first lecture, I'm just going to give a brief introduction to the subjects we're going to cover. We start by looking at the general requirements for the construction site electrical system. This includes defining what a competent person is, and the design documentation required on site. We then go on to how we inspect electrical site equipment, and we go through some examples of good and bad practice. We then look at how we install an electrical site system, starting with a generator compound, then going on to how we install the LV boards. In the next section we look at grounding. We start by going back to first principles and looking at what happens when we have a fault in an ungrounded system. We then use this scenario to compare it to a grounded system and look at the differences between the two. We then go on to look at the different ways we install a ground system on site. In the first scenario, we use the cabling system to connect the ground network. Finally, we look at an alternative way to ground the network, which is to ground each individual panel. In the next section, we look at site electrical circuits. We start by describing a typical electrical system on site, containing a generator, a laydown area, and a distribution system. We then look at all the individual elements separately, starting with how we connect a generator, and finishing with a site distribution board. In the next section, we look at residual current devices, which are one of the key safety features of a site distribution system. We start by going back to first principles, looking at how a residual current device or RCD operates. We then look at how an RCD is constructed and how it deals with a fault. Next, we look at the key features of an RCD. And finally, we look at the key things you need to consider when positioning an RCD in the distribution network. In the next section, we look at electrical faults. We start by looking at a healthy three-phase network and how the currents behave in a balanced and an unbalanced system. We then look at the different possible faults that can occur and see what happens to the currents under each scenario. We then look at the effects of an electrical fault on the human body, starting with the main hazards, before looking at how the effects on the body increase when the current increases. In the next section, we look at how we size an electrical system, starting off with the circuit breakers. Next, we provide a simple methodology for sizing the circuit breakers to feed a typical site office, and also introduce the principle of electrical diversity. We then go on to size the circuit breakers in a main distribution system, before finally looking at how we size a generator. In the next section, we look at electrical cabling. We start by seeing how we size an electrical cable, based on the current that it carries and the volt drop. We then look at how we install cables safely on site, and provide some examples of poor workmanship, before finally looking at the different options of how we take a cable across a roadway. In the final section, we look at lock and tag systems. These are critical to the safe operation of the electrical system on site. We start by looking at the lock and tag system itself, including the tag and the padlock. We then go on to see how we use the lock and tag system to lock off enclosures. Next, we look at isolation points and how we need them in the electrical distribution system to keep the system safe. And finally, we see how we use lock and tag systems to energize a system for the first time. By the end of this course, you will understand all of the basic systems that we use for the construction site electrical system. I hope you enjoy the course. Welcome everyone, my name's Stephen Brooks and I've created the Construction Site Electrical Systems course. I've tried to write the course to make it accessible to everyone, including people without an electrical engineering background. This particular section introduces the basics behind how we install and operate a typical construction site electrical system. I hope you enjoy the section and get something out of it. The aims of the course today are to define the basic requirements for a safe electrical site system, to show what is required for a containerized generator installation, to show how to set up an inspection regime for the site's electrical system, only electrically competent persons are allowed to install or modify any electrical system on site. An electrically competent person shall have a recognised electrical trade qualification from the certifying body of their home country, have a minimum of 5 years relevant experience, have passed a site-based electrical competency test, every project office should have the following documentation: a single line diagram showing an up-to-date version of the site system, all electrical boards and breaker ratings, the location of all RCDs, the length, size and letter tag of each cable, a sizing calculation sheet for the laid-on area and offices, an initial fault calculation for the system, a sizing sheet for each cable, and finally a sizing calculation for the site generator or supply. The site electrical system is to be tested before being energised for the first time and every 3 months afterwards. This shall include visual checks to make sure that the equipment is as per the design and has not been damaged or altered. Look for scorch marks, cuts in cables, or new cables being added without permission. Load and voltage measurements to make sure the equipment is not overloaded. Electrical continuity and insulation checks on cables and distribution boards to check their integrity. Operational tests on RCDs to make sure that they're working, i.e. push the test push button. Here are some examples of the issues the electrical inspections should be identifying. Your electrical audit should go around all the offices and inspect all of the sockets, conduits and electrical equipment to make sure they're installed properly, haven't been modified and are of good quality. You need to look for any damaged or unterminated electrical cables. All damaged cables should be replaced. Identify any exposed wiring on site. This all needs to be covered up to make sure it's not a danger to personnel. Make sure that all the electrical equipment is stored properly. All equipment in stores needs to be inspected and tagged. Any defective equipment should be stored separately in a segregated defective equipment area. And finally, identify any damaged or burnt equipment. Take the equipment out of service and investigate why the equipment is burning. Here we have a typical containerized generator. The generator should be of a good quality, well maintained, and have built-in sound insulation to minimize noise to nearby personnel. The generator should be located inside a sealed concrete bund to catch any diesel or oil leaks and spills. The bund should be labelled with its capacity in litres. This should be at least 110% of the fuel tank capacity. A box should be provided for earplugs. A must-wear hearing protection sign should be provided. Adequately sized fire extinguishers should be located on the edge of the bund. A no smoking within 25 metres sign should be provided. A danger, electrical hazard sign should be provided. Electrical boards should have the following minimum features. Indoor boards can have a wooden or metal enclosure. Outdoor boards must have a metal enclosure, as wood gets damp when it rains and the board becomes hazardous. The board should be locked at all times, and if padlocked, shall have an electrician's tag. The electrician shall keep the keys to all the electrical boards in a locked key cabinet in his office. The board should be labelled and have a diagram showing the circuits being supplied. All external openings should be closed off to prevent vermin access. Here are the features of a good office electrical board. Firstly, the board has a unique number to identify it. All spare circuit breakers are blanked off, so the live terminals behind are kept safe. All circuits are labelled. And finally, the board is lockable. And here's an example of a good quality site board. Again, the board has a unique label to identify it. We have a danger label on the front warning people not to touch it. The board is locked with a padlock and an electrician's tag. And finally, the board is of a solid, well-built construction that will last the full length of the project. Here are some of the main issues we find with poor quality electrical boards. Firstly, we see no labelling on the board. Danger labels are missing, and the separate circuits are not identified. Another thing we see widely is boards that are not kept locked, or where keys are kept in the board, making the locks useless. All boards must be locked, and the keys kept in a locked key cabinet in the electrician's office. The live buzz bars and terminals are exposed because blanking plates have not been provided. This puts anyone opening the board in danger. These boards are of poor quality construction. In the first example, the circuit breakers are loose and there's large openings at the bottom of the board which will let vermin in. In the second example, non-waterproof domestic sockets have been used outdoors. Also, the board is made of wood, which will get damp in the rain and become hazardous. And finally, again, domestic sockets have been used outdoors, which isn't allowed. Most of the problems identified on these slides are common sense. If something doesn't look right, then it probably isn't safe. So take some action and change it. Double insulated power tools are the only type allowed on site. They are defined as double insulated tools as they have 2 layers of insulating material around all live parts and don't have a metal casing, making them far safer than single insulated tools. Because of their construction, this type of tool does not need a ground connection and does not therefore have a ground wire. Double insulated tools always have the following symbol on their body or manufacturer's label. Single insulated tools are banned on site. They can be usually identified due to their metal bodies. Here are some examples. "110-volt mains operated tools are the only ones that can be used on site. 230-volt tools are banned. Battery operated tools are an ideal alternative, as they remove the need for site electrical boards, extension leads, electrical cabling, and also reduce the size of the site generator. Special permission is required from the electrical utility before work begins near overhead lines. Height barriers may need to be installed as required. All cranes and equipment working near overhead lines should be grounded with a copper ground rod driven deep into the earth. Before you start work at a location that has overhead lines, contact the local electrical utility and get some advice on how to proceed. They will normally send someone down to discuss the works with you and let you know what works can be done and whether any height barriers or working restrictions are required. Care may also be needed when storing materials near live overhead lines, especially metal objects or coils of wire, as electrical energy may be induced into the materials from the live line. Let's summarize what we've learned today. Only competent electrical persons can install or modify electrical systems on site. Every office should have electrical design documentation, including a single line diagram and sizing calculation sheets. All containerized generators should be housed in a bund and have signage and fire extinguishers as per the standard. Electrical boards should have a metal enclosure when outdoors, and be of good quality, be kept locked at all times, and have external openings sealed. Congratulations for completing the Site Electrical Systems module. I know we've covered a lot of ground today, so take some time to go back and do some of the course again. I've attached some questions on today's section to test your knowledge. In this section, we will look at electrical grounding on site. Grounding is a key safety feature of any electrical system, and is particularly important on construction sites, where we have hazards associated with the construction process. By the end of this section, you'll understand why we need a grounding system, and the different ways in which a grounding system could be installed. The aims of the course today are to explain why we have grounded systems, to look at the different options for a site ground system, to look at some poor quality ground systems, a grounding system, or in some parts of the world called an earthing system, is there to protect equipment and personnel from the dangers of electrical energy, and to dissipate the fault current when things go wrong. Let's look first at an electrical system that is not grounded. The first thing to know is that the ground beneath your feet is normally at 0 volts. It has no voltage potential and can be used as a reference point to all other voltages. In this case, the source of the electricity is an AC generator. Here we have the same generator as before with a live and neutral. If we look inside the generator, we will see a winding across which the electricity is formed. When the generator starts operating, a voltage appears across its live and neutral terminals. If we now connect a load, current will flow from the live terminal, through the load, and back through the neutral. What happens if the live conductor becomes disconnected and drops to the ground? For a short time, the ground voltage around the conductor will rise to match the live voltage. Some current will flow till the ground and generator voltages equalize. Eventually, the voltage on the generator terminals will collapse and the generator will switch off, disconnecting the fault. Let's now look at an electrical system where the generator is grounded. Here we have the same generator as before with a live and neutral. This time we ground the generator by connecting the bottom of the generator winding, called the neutral point, to the ground system using a solid copper ground rod. Let's see what happens this time when the live conductor drops to the ground. Again, for a short time, the ground voltage around the conductor will rise to match the live voltage. This time we have a circuit, from the live terminal, through the fallen conductor, through the ground, and back into the generator through the ground connection. The resistance of this circuit is quite low, as it only consists of the conductor resistances and the resistance of the ground. This low resistance path results in a very large current flowing from the generator into the ground. The generator will detect the large current and quickly switch off, disconnecting the current. Therefore, in a grounded system, a high level of current flows when a fault occurs. This example clearly shows the difference between grounded and ungrounded systems. When a fault occurs, the grounded system detects the current increase immediately, disconnecting the electrical supply and making the system safe. In the ungrounded system, we don't have this option, as there is no increase in current and the fault therefore remains in place, putting personnel and equipment in danger. This is the main reason that we always ground electrical systems. All site electrical systems must be grounded so that we can quickly detect when things go wrong by monitoring the current levels. A higher than expected current level indicates that there is a problem. All generators and transformers have their neutral points grounded to provide a path for the fault current. All metal enclosures containing equipment must be grounded to provide a low resistance path for any fault current, which will then flow through the ground back to the generator neutral point. There are two common ways to provide a grounding system for a construction site. The first option is to provide a ground system through the power cables. Here we have a typical three-phase site generator. We ground the neutral point of the generator. We then run a ground wire through the electrical power cables and connect it to the ground terminal in each electrical panel. If a fault does occur, the fault current will flow back through the ground wire back to the generator neutral point. The second option is to ground each of the electrical panels individually. Here we have our three-phase generator from before. Again, we ground the generator neutral point. We then ground each electrical panel with its own ground rod driven into the earth. If a fault does occur, the fault current will flow back through the earth, back to the generator neutral point. These are the two common ways that we can provide a ground system for an electrical network on site. The direct cable connection method tends to be used when the site is located near to the generator. Once the distance increases, the cost of the grounding cable can be excessive, and the individual equipment grounding system tends to be used. Both methodologies are fine and provide a defined path for any fault currents. We also see a combination of both systems on site, which is acceptable as long as they are tied together to provide one grounding system. Whichever ground system we use, all cable ground wires must be connected. Here's some examples of where cable ground wires were deliberately removed. Any sites found that don't have a ground connection will be switched off. Two-pin ungrounded sockets are not allowed on site, as they do not provide a ground connection for equipment that needs it. Let's summarise what we've learned today. All construction sites must have a solidly grounded electrical system, which allows them to detect faults when they occur and provide a voltage reference point. On construction sites, all generators must have their neutral points grounded. There are two ways to provide a grounding system for a construction site. The first option is to provide a ground system through the power cables. The second option is to ground each of the electrical panels individually. You've now completed two modules, and you should now be familiar with grounding system. This section has covered a difficult topic, so please go back and redo the parts that didn't make sense, as understanding grounding is essential for the safety of the construction site electrical system. I've attacked some questions on today's section to test your knowledge. Well done for making it halfway through the course. In this section, we will introduce residual current devices. We will start from first principles and see how residual current devices operate and why we need them, before going on to see how they are installed in the site electrical system. The aims of the course today are to introduce residual current devices, or RCDs, to show how RCDs operate, to show where RCDs should be located in the electrical system, let's think of the electrical system in terms of flowing water. Here we have the generator. This is the pump pumping the water around the system. We have a pipe representing the live conductor. The water flows from the generator through the live pipe. We have a load, which uses up the energy of the water. And finally, we have a neutral pipe taking the water back to the pump. Let's now start pumping the water around the system. The water flows through the live pipe, through the load, and back through the neutral pipe. The water flows quickly through the live pipe. The energy of the water is then used up by the load, and then the water flows slowly back through the neutral pipe. Let's now summate the amount of water flowing through the live pipe and flowing back through the neutral pipe. Some of the water, or current, is zero, because the same amount of water flows through the live pipe as flows back through the neutral pipe. Let's now see what happens if a leak occurs. There's now a difference between the water flowing through the live pipe when we compare it to the water flowing back through the neutral pipe. Therefore, the sum of the water no longer equals zero. We can therefore use this principle to quickly detect if there's a leak in the system. The device that measures the current in the live and neutral is called a residual current device, or RCD. Here we have a circuit with a live and neutral feeding a load. The current flows through the live conductor, through the load, and back through the neutral conductor. We have a measurement winding which summates the current flowing through the live and back through the neutral. When the live and neutral currents are balanced, no current flows through the measurement winding. We therefore know that there's been no leaks and the system is healthy. Let's now add a ground fault. Some of the live current now flows through the person into the ground. Some of the current is leaked away. The live and neutral currents are now no longer balanced, and current flows in the measurement winding. We've therefore detected that the system has a leak and we can do something about it. Residual current devices are a very simple and quick way of detecting any electrical fault. When the system is healthy, no current appears on the detection winding. As soon as a fault occurs and some current starts leaking out, the detection coil will go out of balance and current will flow. RCDs are provided to protect personnel. They therefore normally operate at a low current level, normally 30 milliamps or less, which is the current level at which damage is done to the human body. RCDs can be identified by the following symbol. Here's a single-phase RCD, with the measurement winding summating the live and neutral. Here we have a three-phase RCD, with the measurement winding summating the red, yellow, blue, and neutral windings. When looking at an RCD, we can see the following features. A test push button. When pressed, this simulates a fault and trips the RCD. The RCD bubble symbol. The RCD needs all three phases and the neutral to operate successfully, so there are 4 terminals, or 2 for the single-phase RCD. The milliamp current rating of the RCD. This is normally 30 milliamps or less, to protect personnel. The decision of where to put the RCDs depends on what's connected to the board. You must put RCDs on any electrical board that feeds a wet area. This includes bathrooms, toilets, water chillers, pumps, and wet concrete cutting areas. Hand tools or machinery, i.e. construction sites or workshops. Exposed cables or extension leads, i.e. on all site electrical boards. There are several options of where to put RCDs in a site electrical system. Here's a typical site electrical system, with a generator, a main distribution board, and some sub-distribution boards. Option A is to put the RCD on the main board incomer. Option B is to put RCDs on all the main board feeders. Option C is to put RCDs on all the distribution board incomers. And finally, option D is to put RCDs on all the distribution board feeders. Let's look at option A first, putting RCDs on the main electrical board incomer. The disadvantages are: the RCD will trip the whole of the site for a fault anywhere in the system. We therefore have very poor fault discrimination. The RCD will be sensitive to maloperation because all of the trace ground currents for the whole site are detected at this point. The benefits are: the RCD covers the whole system. There's no gaps. This is an inexpensive option. We only need one RCD for the whole site. Let's look at option B, putting RCDs on the main board feeders. The disadvantages are: this still trips a large part of the electrical system for a single fault. And again, detection is still far away from the likely fault. The benefits are: if you put an RCD on each feeder, we will cover the whole system. This is an inexpensive option. The RCD is only needed on a small amount of feeders. Let's look at option C, putting RCDs on the distribution board incomers. The benefits are: the RCD only trips the faulty board. We have better discrimination. This is an inexpensive option. We only need RCDs on a small amount of feeders. Because of these benefits, this is the most common place to put RCDs on the site system. This is the best place to put RCDs, as the competent electrical person can look at each board and, depending on what's connected to it, decide if an RCD is required on the incomer or not. If a fault does occur, only the faulty board is disconnected, so the fault can be quickly identified and cleared without disruption to the rest of the users on the system. Finally, we have option D, put RCDs on all the distribution board feeders. The disadvantages of this are: this is an expensive option. Lots of RCDs are required. The benefits are: the RCD only trips the faulty feeder. We have really good discrimination. Let's summarize what we've learned today. Residual current devices, or RCDs, measure the live and neutral currents to check if there's an imbalance. Once the imbalance reaches a certain point, the RCD will operate, protecting personnel from hazardous currents. The position of the RCD needs to be chosen carefully to protect the areas necessary, but avoiding unnecessary disconnection of healthy circuits. You've now completed 4 modules. You should now be familiar with residual current devices and understand why we need them, and where to put them in the site electrical system. This section has covered one of the most important devices that we use in the site's electrical system, so don't hesitate to go back and redo the elements that didn't make sense. I have attached some questions on today's section to test your knowledge. In this section we will look in detail at all the different types of electrical circuits that you will come across on any typical construction site. We start by looking at the connections inside the electrical generator, and then go on to look at the circuitry of the distribution and subdistribution panels. The aims of the course today are to show the basic features of a site electrical system, to look at how a generator is connected, to show how an electrical distribution system should be installed, here we have a typical site electrical system. Firstly, we have the containerized generator. This is normally a three-phase device operating at 415 volts. We connect the generator to a site isolation switch. This has the ability to disconnect the whole site electrical system in case of maintenance requirements or an emergency. We then have the site generator board, which feeds power out into the network. We tend to have two main electrical systems on site. The first is the laydown area, where all the project offices are located. The second area is the site distribution system. We tend to have one main board, which then feeds all of the individual site subdistribution boards. Let's now look at all these individual elements in more detail. Let's now look inside a typical three-phase site generator. Here's a single line diagram for a three-phase generator, with red phase, yellow phase, blue phase, and neutral. And here we show the actual connections for the site generator. The four cables at the top, the red, yellow, blue, and neutral cables, connect directly to the generator alternator. We then have the generator circuit breaker. This protects the generator from any external faults, and is set to trip if the maximum current drawn by the system exceeds the rating of the generator. The generator circuit breaker switches the red, yellow, and blue phases. The neutral connection is not switched by the circuit breaker, and instead has a disconnecting link. Here we have the three-phase cable connecting the red, yellow, blue, and neutral phases to the distribution system. The generator must be grounded. This is done by connecting a ground cable to the neutral point of the generator and connecting this cable to a copper ground rod driven into the ground. The isolation switch is there to disconnect the electrical system to the site in case of maintenance or an emergency. Here's a picture of a typical isolation switch. Let's now see how the switch is connected. The first thing we do is ground the metal enclosure of the isolation switch. We do this with a copper ground rod driven into the ground. The isolation switch disconnects the red phase, yellow phase, blue phase, and neutral, and has to be rated to carry and break the full site current. We have the three-phase cable from the generator, with a red phase, yellow phase, blue phase, and neutral. We then have a cable connected to the isolation switch to the generator panel. The site isolation switch is an important element of the electrical system, as it is often the only way that the site personnel can switch off the power in the event of an emergency. It is important that it's clearly labelled and located in an accessible position and that everyone knows where it is. You also need to ensure that the switch is never locked in the on position. As the generator has its own circuit breaker, the generator electrical board is simply there to feed the electrical supplies out to the site electrical distribution system. Firstly, the board should be grounded using a copper earth rod driven into the soil. We have red, yellow, blue and neutral bus bars. These carry the electricity from one point to the next. We have the cable to the isolation switch. We then have feeder cables to connect the three-phase power to the site distribution system. Now let's look at the site main electrical distribution board. Firstly, the board should be grounded using a copper earth rod driven into the soil. We have the cable from the generator panel, bringing the three-phase supply into the board. This connects to the incomer circuit breaker, which switches the red, yellow and blue phases. The neutral wire is connected to the common neutral terminal strip. We have some three-phase feeder circuit breakers. We now loop across the red phase from the incomer circuit breaker to the feeder circuit breakers. We then loop across the yellow phase and the blue phase. We have the feeder cables to take the three-phase power to the site distribution system. We then connect the red phase, yellow phase and blue phase to the feeder breaker for that circuit. We connect the neutral to the common neutral terminal strip. And finally, the site sub-distribution board. We ground the board and this time we connect it to a ground terminal strip. We have the cable from the main distribution board to bring three-phase power into the sub-distribution board. Again, we have a three-phase circuit breaker on the incomer. The neutral wire is connected to the common neutral terminal strip. The feeder circuit breaker is a single phase, as they only need to switch the live connection. Our aim is to balance the loads on the three-phase system, so we connect two breakers to the red phase, two breakers to the yellow phase, and two breakers to the blue phase. The feeder sockets are connected to the live via the circuit breaker, the neutral terminal strip, and the ground terminal strip. The main difference between this board and the main distribution board are the connections to the neutral and ground terminal strips. These are required as we are now supplying single-phase supplies to the sockets. When installing the neutral and ground terminal strips, make sure that there are plenty of spare terminals for future cables, and never connect the neutral and ground systems together. Let's summarise what we've learned today. A generator should always be grounded by connecting a ground cable to the neutral point. A main site isolation switch should be provided to disconnect the electrical system in case of an emergency. In a distribution board, the neutral wires are all connected to the neutral terminal strip, the ground wires to the ground terminal strip, and the live wires to the circuit breakers or bus bars. You've now completed 3 modules. You should now be familiar with electrical circuits and systems you find on any typical construction site. I've attached some questions on today's section to test your knowledge. In this section we will look at electrical faults. We obviously design our site electrical system to operate correctly and safely, but sometimes things go wrong. So we need to understand how electrical faults occur and what the implications are on personnel when they do. The aims of the course today are to show what an electrical fault is, to look at the different types of faults, to show the hazards of electricity, let's see how an electrical system behaves during a normal condition. Here we have a three-phase generator with a red phase output, a yellow phase output, a blue phase output, and a neutral output. The first thing that we do is ground the neutral point. Here we have a three-phase load. We connect the generator to the load with a red phase conductor, a yellow phase conductor, a blue phase conductor, and a neutral conductor. During normal three-phase operation, we have a red phase current, a yellow phase current, and a blue phase current. All of these currents combine together and come back to the generator via the neutral conductor. The neutral current that flows is the vector sum of all three-phase currents. Here we have the three-phase currents, red, yellow, and blue, separated by 120 degrees. All three-phase currents have the same magnitude. We therefore define this as a balanced load. On the neutral, all these three currents come together. Let's now add them together and see what happens. Because all three-phase currents are identical in magnitude and are 120 degrees apart, they all cancel each other out. Therefore, in a balanced three-phase load, the neutral current equals 0. Let's now look at an unbalanced load. In this scenario, the blue phase current has a lower magnitude than the other two. Again, on the neutral, all three currents come together. Let's now show that. This time, because the blue phase current has a lower magnitude, there is now a spill current on the neutral. Therefore, in this scenario, some current flows through the neutral. The implication of this is that we need to consider the neutral conductor as a live conductor, as it sometimes carries current. This is the reason that we make the neutral conductor the same size as the phase conductors. In a single-phase system, the neutral current is the same as that which flows through the live conductor. In a three-phase system, the current can range from 0, for a perfectly balanced three-phase system, right up to the full-phase current when only one phase is loaded. The neutral conductor therefore needs to be considered just as dangerous as the live conductor as it carries current. Let's now see what happens if the blue phase conductor touches the ground. This time, instead of the blue phase current going onto the load, it goes through the conductor, through the fault, through the ground, through the generator ground connection, and back to the generator neutral point. This path has a lower resistance than going through the load, therefore the current increases substantially. This scenario is called a ground fault. This time, let's see what happens if the red phase touches the neutral. In this scenario, the red phase current again does not go through the load. Instead, it goes through the red conductor, through the fault, and back down the neutral conductor. This path has a much lower resistance than going through the load, therefore the current will increase substantially. This is called a phase to neutral fault. And finally, let's see what happens if the yellow and blue phases touch together. This time we have what's called phase-to-phase currents that flow between the blue and yellow phases. Again, the current will increase substantially, as this path has a lower resistance than going through the load. This is called a phase-to-phase fault. There are obviously an infinite number of possible faults that can occur, but these are the three main types. In all of these faults, the current should increase, and this will be detected by the circuit breakers, which will then operate and stop the electricity flowing. For higher voltage systems, we use a dedicated system called secondary protection, which can detect which type of fault is occurring before taking the appropriate action. This will be discussed in detail in a separate course. Things to be aware of. The fault current is limited by the capacity of the generator, but can exceed 40,000 amps in an LV system. There are many types of fault. The main ones are phase to neutral, with no resistance, phase to ground, a conductor falls onto the ground, and phase to phase, where two live conductors touch. The longer the fault stays in place, the more damage is done, so it needs to be detected and removed quickly. This is done by circuit breakers. The main hazards when electrical faults occur are fire and explosion, as the electricity has a huge amount of energy. Electric shock. You can have held on. When a person grips the conductor, the muscles automatically contract and the person can't let go. Or not held, when a person is thrown away from the fault. Electric flash. This mainly affects the eyes. Electric burns. These can be dual burns which are inside the body, or flash burns which are outside the body. As the current flowing through the body increases, the effects also increase. For the current between 0.5 and 3 milliamps, there will be minimal effects, including tingling sensations. For the current between 10 and 40 milliamps, we have the let-go threshold. Above this, the muscles contract and the person can't let go of the live conductor. Between 30 and 75 milliamps, things get more serious. We can have respiratory paralysis. This is when the muscles contract and people find it difficult to breathe. Between 100 and 200 milliamps, we have ventricular fibrillation. This is when the heart starts beating erratically. Between 200 and 500 milliamps, the heart clamps tight and people lose consciousness. Above 1500 milliamps, tissue and organs start to burn. We can see that above 30 milliamps, the hazard to personnel increases significantly. This is why we set most RCDs to a 30 milliamp level. This protects personnel from danger. Let's summarise what we've learned today. If something goes wrong with the electrical system, this is called an electrical fault. Electrical faults need to be detected and cleared quickly to protect equipment and personnel. Above 30 milliamps, an electrical fault causes serious hazard to personnel. RCDs are set at this level to protect people from harm. You've now completed 5 modules and should now be starting to understand all of the basic principles that we use to design and operate the construction site electrical power network. I've attached some questions on today's section to test your knowledge. In this section, we will provide some basic principles of how to size the circuit breakers that make up the site electrical system. We also introduce the principle of electrical diversity and provide some simple guidance of when and how to use it. The aims of the course today are to show how to design a typical site electrical system, to show how electrical diversity works, to provide a way of sizing circuit breakers, Here we have a typical site electrical system for the laydown area. Firstly, we have the generator, which is connected by cable to a main distribution board, which then feeds some site offices. The question is, how do we choose the rating of the circuit breakers? Firstly, let's look at a typical site office. Here we have the same type of containerized site office you'll find on any site. Each office has its own electrical board. This feeds a couple of lights, one in each office. Two ACs, again one in each office. We then have a couple of sockets in each office, used for computers and other office equipment. And two fans, one in each toilet. Let's now see how we size the electrical board. Let's calculate the loads in the site office. Firstly, we have 4 sockets, 2 in each office. Typically rated at 8 amps, that gives you 32 amps. We have the lights. These are rated at 60 watts. Using our standard power equation, the power equals the voltage times by the current times by the power factor, which in this case we'll assume is 0.8. Therefore, transposing the equation, the current equals 60 watts divided by 0.8, which is the power factor, multiplied by 220 volts, equals 0.3 amps. Therefore, for 2 lights, the current drawn will be 0.6 amps. The fans have a slightly lower power demand. They're typically rated at 20 watts. Therefore, using the same power equation, the current equals 20 watts divided by 0.8, which is the power factor, multiplied by 220 volts, equals 0.1 amps. Therefore, for 2 fans, the current drawn from the system is 0.2 amps. The air conditioning units tend to be the biggest load in the office and are rated up to 1 kilowatts. Therefore, using the same power equation as before, the current equals 1000 watts or 1 kilowatt divided by 0.8, which is the power factor, multiplied by 220 volts. Therefore, the current for 1 unit is 6 amps. For 2 air conditioning units, the current drawn from the system is 12 amps. Let's now add all these loads together. The total load for one office equals 32 amps, plus 0.6 amps, plus 0.2 amps, plus 12 amps, equals 44.8 amps. The question is this realistic? To make it more realistic, we need to apply some diversity. Diversity is a way of applying common sense and using our knowledge of the system to give us a more realistic figure of what the load drawn from the system might be. Let's look first at lighting. Is it likely that both lights will be on at the same time? Yeah, of course it is. When it gets dark, both lights may be on. Therefore, we apply 100% diversity, which means we use the full load. What about the air conditioning? Is it likely that both air conditioners will be running at the same time? Of course it is. So therefore again we apply 100% diversity, which means 100% of the running load. What about the toilet fans? Is it likely that both fans will be on at the same time? Of course. Therefore again we apply 100% of the running load. And finally, what about the sockets? Is it likely that all the sockets will be fully loaded and drawing 8 amps from the system all the time? No, of course not. The socket load depends on what's plugged in, but it's very unlikely that all the sockets will be fully loaded. Therefore we apply some diversity. A common diversity principle we apply is to use 100% of the first socket rating and 40% of the rest. Let's now use this diversity factor in our previous equation. There is no standard on what diversity factor you need to apply. It really comes down to your knowledge of your own system. When designing a system, write down what diversity factor you've assumed and why. When the system is energized, monitor the current levels of various points to make sure that your diversity assumptions were correct. If the current is widely different to what you assumed, then change your diversity factor on the next design. Let's apply some diversity to the loads in the site office. Firstly, for the sockets. As we've said, we apply a diversity factor of 100% of the first socket rating and 40% of the rest. Therefore, putting this in the equation equals 100% of 8 amps plus 40% of the other 3 sockets equals 17.6 amps. For the lights, we apply 100% diversity factor. Therefore, as before, it equals 0.6 amps. For the fans, the same. So as before, it's 0.2 amps. And finally, for the air conditioning units, that's 100% as well. That gives you 12 amps. Therefore, the new total equals 17.6 amps plus 0.6 amps plus 0.2 amps plus 12 amps equals 30.4 amps. This is a more realistic figure. Therefore, let's go for a 32 amp circuit breaker for each office. So here's the full site electrical system from before. So we've now made each of the office circuit breakers 32 amps. How do we size the source circuit breakers that feed them? These are the basic rules that we need to apply. Source breakers should never be rated less than the breakers they feed, as the current flowing into the top of a cable equals the current flowing out the bottom. The difference in the two ratings should be kept to a minimum, so that faults can be dealt with quickly. So for the source breakers, a logical solution is to make them all the same rating as the office breakers. So therefore, let's make them 32 amps. What about the board incomer breaker? Well, let's use our common sense again. Is it likely that all 5 feeders will be fully drawing 32 amps all the time? No, of course not. Therefore, let's apply some diversity. Using the same factor as before, we have 100% of the first feeder rating plus 40% of the rest. Putting the numbers in now, that equals 32 amps for the first feeder and 40% of the rating for the other 5 feeders, which equals 96 amps. Therefore, let's choose a 100 amp circuit breaker. We've now sized all of the breakers on the electrical system using our knowledge of the system and some common sense. Let's now look at a typical site electrical board. These are 16 amp sockets. The question is, do we have any control about what's plugged into the socket? The answer is no. Anyone can come along and plug anything into the socket, which may load the socket right up to its full rating of 16 amps. Because of this, we have no choice. We have to make all of the feeder breakers 16 amps to match the socket. What about the rating of the incomer? Is it likely that every single socket will be fully loaded at 16 amps all the time? Of course not. Therefore, we need to apply some diversity. Again, size the incomer circuit breaker using a diversity factor of 100% of the highest feeder rating and 40% for the others. Therefore, 100% of the first feeder rating is 16 amps, plus 40% of the rest, equals 54 amps. Let's choose a 63 amp circuit breaker for the incomer. We've now sized all of the breakers on a site electrical board. Let's now size the full site system. As usual, for feeders, make the rating the same as the remote end breakers, as the current flowing into the top of the cable is equal to the current flowing out of the bottom. We therefore make the feeder breakers 63 amps. For the incomer, apply a diversity factor of 100% of the highest feeder rating and 40% for the others. Therefore, equals 63 amps for the first feeder and 40% of the rest, equals 163 amps. Based on this, let's choose a 180 amp incomer circuit breaker. Let's see how we size a generator. The best way to do this is size it based on the incomer circuit breaker rating, as this has already been sized for the full loads on site. Therefore, using our standard power equation, the power equals 1.73 times by the line voltage, multiplied by the phase current, multiplied by the power factor, which we'll assume as 0.8, equals 1.73 times by 380 volts, times by 180 amps, which is the incomer circuit breaker rating, multiplied by 0.8, equals 95 kilowatts. It's good practice to make the generator larger to allow for future loads and starting currents. Based on this, let's choose a generator rating of 120 kilowatts. You always need to supply a generator with some spare capacity to allow for the site system expanding in future and the starting and inrush currents which happen as all of the equipment will energise at the same time when you turn the generator on. You also have to ensure that the generator is not too lightly loaded, as running it at a load way below its rated capacity, less than 30%, can actually damage the generator. Let's summarise what we've learned today. We need to use a logical methodology to size all of the circuit breakers in an electrical system. Source circuit breakers can be rated the same as the destination circuit breaker that they feed. We can use diversity to size circuit breakers when the loads that they feed are not fully utilised. You should now understand how the principle of electrical diversity works and how to apply it to size circuit breakers in a site electrical system. I have attached some questions on today's section to test your knowledge. In this section, we will look at electrical cabling on site. We will start by looking at how we size electrical cables using the current rating and volt drop, before seeing how we can install and operate electrical cables safely on site. The aims of the course today are to show how to install cables safely on site, to show how to size a power cable based on the current and the required volt drop, to show how to connect cables together safely, to show how to install cables when a roadway is involved, to select which cable we want to use, we need to look at the data tables from the cable manufacturer. Here we have a typical cable data table. The table shows the cross-sectional area in millimetres squared, the maximum continuous current carrying capacity in amps, and the resistance per metre in ohms. we can see that as the cable cross-sectional area or size increases, the resistance per meter decreases. As the cable cross-sectional area or size increases, the current carrying capacity increases. We can use this data together with the system parameters to work out which cable we need to select for any application. Let's do a worked example. For a circuit that will carry 128 amps continuously, choose the correct cable. Here we have the table from before. All we need to do is go down the table and select a cable that can carry the current required. From the table we can see that a 50 square millimeter cable is suitable, so that's the one to go for. We always choose a cable that can carry more than the required load, so we could in theory choose a 70 square millimeter cable as well. We can see from the table that each cable also has a resistance per meter. Let's call it RC. This is a linear relationship, so as the cable gets longer, its total resistance increases by the same amount. Therefore, for a cable 3 times longer, the resistance will be 3 times higher. Let's now look at a typical circuit. Here we have a standard circuit with a live, a neutral and a load, with current flowing and voltage V source at the input. In this ideal condition, the voltage at the load, V load, equals the voltage at the source, V source. In practice, we need to consider the resistance of the cables that carry the electricity from the source to the load, RC. The cable carries current and has a resistance, therefore it must generate a voltage across it from Ohm's law. This results in the voltage at the load, V load, being less than the voltage at the source, V source. This difference is called the cable volt drop. Let's do a worked example. Using the data table, select a 125 meter long cable that can carry 92 amps and keep the cable volt drop below 10% of the source voltage of 230 volts. Step 1 is to select a cable from the table based on its current carrying capacity. Here's the cable data table from before. Looking at the table, a 25 square millimeter cable can carry 92 amps. Let's choose that one. Step 2 is to calculate the cable volt drop. From Ohm's law, voltage equals current times by resistance. Resistance equals cable length times by the cable resistance per meter. Here's the cable data table from before. We can see from the table that for our 25 square millimetre cable, the resistance per metre is 0.000727 ohms. Let's put that into the equation. Resistance equals 250 metres, which is the cable length, multiplied by 0.000727 metres from the cable table, equals 0.181 ohms. Therefore, volt drop equals 92 amps, which is the cable current, multiplied by 0.181 ohms from above, equals 16.65 volts. This means that the voltage at the end of the cable will be 16.65 volts less than the voltage at the start of the cable. Step 3 is to calculate the volt drop percentage. Percentage equals 16.65 volts from the equation above, divided by 230 volts, which is the source voltage, equals 7%. Therefore, a 25 square millimetre cable is okay. What would we have done if the volt drop had been over the 10% value shown? Well, we would have chosen the next cable size up, as it has a lower resistance and therefore a lower volt drop. Most of these calculations can now be done using software supplied by the cable manufacturers. All cables on site should be connected together using waterproof, colour-coded, industrial standard sockets. The colour of the plug-in socket depends on the voltage level. For a voltage of 110 volts, the plugs and sockets are yellow. For a voltage of 230 volts, the plugs and sockets are blue. And finally, for the voltage of 415 volts, the plugs and sockets are red. Only industrial standard extension leads can be used on construction sites. Domestic standard extension leads are not sturdy enough and will get damaged. Homemade extension leads or connector boxes are not allowed. Here are some examples of some poor quality extension leads. Unless you can see both ends of an electrical cable or wire, you should always assume that it is live, and therefore dangerous. All unterminated cables and wires are to be removed from site. Tape joints should never be used on cables as the glue fails, leaving the live conductors exposed. Here's some examples of some poor quality tape joints. The only solution is to use a proper heat shrink connection. Above ground, the industrial standard socket should be used to join cables. Below ground, heat shrink joints are the way to go, as they provide a permanent, waterproof joint which has a similar mechanical integrity to the original cable. Cables should be kept off the floor at all times. This keeps them out of standing water, removes them as a trip hazard, and stops them being damaged. The best solution is to run the cables above head height using the building structure. Here's some examples of where the cables are being exposed to damage and have also become a trip hazard. Electrical cables cause a particular hazard to metal scaffolding platforms. If the cable gets damaged and comes into contact with the scaffolding, the whole scaffolding structure will become live and extremely hazardous. When electrical works are taking place on scaffolding, we should ground the scaffolding with a copper ground rod. Try and segregate the cable from the scaffold using insulated hangers and plastic piping. Never wrap electrical cables around scaffolding. When we need to take a cable across a roadway on site, we have several options. Option 1 is to take the cable above the roadway. Here's an example of what we require. Poles are provided on each side of the road and the cable is strung between them. Additional wires may need to be strung between the poles to support the cable and stop it sagging. Option 2 is to go across the roadway surface. We can run a steel pipe across the roadway, then cover it with sand or soil to protect it. We then run the cable through the pipe. If there is only light traffic on the roadway, a cable protector can also be used as an alternative. Option 3 is to run the cable underneath the roadway. To do this, we bury a steel pipe underneath the roadway, then run the cable through the pipe. This is a more permanent solution. Burying steel pipes underneath the roadway is obviously the best permanent solution, and pipes can be installed as the site is backfilled. They can then be used for cabling as the need arises. For temporary situations, either of the other options are fine. Any installation should be checked and tested by the competent electrical person before the cable is energized. Let's summarize what we've learned today. Cable should be selected and sized using their current rating and taking into account the maximum allowable volt drop. Only industrial standard extension leads can be used on site. Domestic and homemade extension leads are banned. Electrical cable should be joined using colour-coded industrial standard sockets. When cables need to cross a roadway, the cable can either be taken above the roadway using poles, beneath the roadway in a steel pipe, or across the roadway using a cable protector. You are now nearing the end of the course and should have a good understanding of electrical cabling and the other elements that go into a site electrical network. I've attached some questions on today's section to test your knowledge. Congratulations for making it to the final section of this course, which looks at lock and tag systems. These are used throughout the electrical network and are of particular importance for site electrical systems, where they are used to control access to and operation of the electrical network. The aims of the course are to define what a lock and tag system is, to see how we create a lock and tag system, to show how we use a lock and tag system on a site electrical system, a lock and tag system is used to control who can access electrical equipment or systems and allows for the safe energization, operation, and maintenance of those electrical systems. On site electrical systems, we use lock and tag systems to achieve the following: to lock off live electrical equipment and make sure that only the competent electrical person has access. To allow the competent electrical person to lock off electrical systems when they need to be maintained, repaired, or modified. To allow the competent electrical person to energize a system for the first time in a safe, controlled manner. We will cover these three scenarios in the remaining parts of this section. All enclosures and isolation points must have a numbered padlock and electrician's tag. Each padlock should be numbered and have a unique key which only opens that lock. If you use a hasp, multiple padlocks can be applied to the same enclosure. All padlock keys should be kept in a lock key cabinet in the electrical competent person's office. The tag should be completed with the electrical competent person's name and contact details. Here we have a typical site electrical system. To prevent unauthorized access to the electrical equipment, all of the electrical housings, boards and enclosures must be permanently locked closed using a key or electrician's tag and padlock. The competent electrical person needs to take control of their electrical system and make sure that no one else can access any live terminals or equipments, make any modifications, or put themselves in harm's way. The only way to achieve this is by locking off all electrical enclosures. We also need to be able to isolate equipment when they need to be taken out of service for repair or maintenance. Let's look at a typical site system. To work on the sub-distribution boards, we need to be able to lock off the incomers. To repair or work on the distribution cabling, we need to be able to lock off the feeder circuit breakers. To work on the main distribution boards, we need to be able to lock off the incomers. To isolate the site electrical system, we need to be able to lock off the site isolation switch. To work on the generator, we need to be able to lock it in the off position. Isolation points for the electrical system are important and need to be considered when the system is designed. Most modern circuit breakers are supplied with a hasp or insert, which allows them to be locked off and isolated in the open position. When we'll energize an electrical system for the first time, we need to follow a set procedure to ensure that no personnel are put in danger. These are the steps to follow. Step 1 is testing. Step 2 is planning. Step 3 is isolation and labeling. Step 4 is energization and monitoring. And finally, step 5 is final configuration. Firstly, we need to make sure that all equipments to be energized are tested as per the approved inspection and test plan, manufacturer's recommendations and agreed standards. We start with the smallest element first, move on to the larger elements, then test the full system functionality. All of the tests should be witnessed and recorded as per the agreed procedures. When the tests are completed The competent electrical person shall certify that the system is ready for energization. Step 2 is planning. The competent electrical person shall now review the full electrical system and agree how it can be energized safely. The review shall decide the isolation points for the equipment, the phase sequence of the energization, and what checks need to be done during the energization. This plan should be written down so that there is no confusion later. Step 3 is isolation and labeling. The competent electrical person shall use a lock and tag system to lock off all of the agreed isolation points. All equipment enclosures are to be locked using a lock and tag system. All equipment to be energized is to be labeled with danger live equipment labels. Step 4 is energization and monitoring. The competent electrical person shall check that the equipments to be energized are ready and that personnel are clear of the area. The competent electrical person shall then remove the isolation locks and tags for the equipment to be energized and energize the electrical system in the agreed sequence and in a controlled way. The competent person shall now inspect the energized equipment to check for any damage and do the necessary measurements. Step 5 is final configuration. Once the full system has been energized, the competent electrical person shall configure the final system as per the site requirements. All circuits not in use should be locked closed using a lock and tag system. All electrical enclosures and equipment doors shall also be locked closed using a lock and tag system. Let's see how we would safely energize a site electrical system in a controlled way for the first time. Here's our site electrical system from before. Firstly, the competent electrical person shall use a lock and tag system to lock off all of the agreed isolation points. Energize the generator, check it's running correctly, and measure the voltage and frequency. We then close the isolation switch and check that the connecting cables are carrying the voltage. Next, we close the incomer circuit breaker and check that it energizes the bus bar. Then, open and close the circuit breaker a few times to check that it's fully operational. We then close and operate the feeder breakers and check that they operate correctly and that the cables can carry the voltage. Finally, we close and operate the incomer circuit breakers in turn and check that they energize the bus bars. Once the system's fully energized, we then lock and isolate all unused equipment for the final configuration. Let's summarize what we've learned today. All electrical enclosures and equipment doors should be kept locked and controlled using a lock and tag system. Isolation points should be defined throughout the electrical system so that the equipment can be disconnected and locked off for maintenance, repair or modification. When the electrical systems are energized for the first time, this should be done in a controlled and planned way under the supervision of the electrical competent person. Well done for completing the electrical power equipment course. I hope you now understand all of the basic elements of the construction site electrical power network, which will allow you to install your own network safely and check that networks installed by others are done correctly. See you on the next course.